Hey everyone, I'll be talking about vision transformers and my research that the research I've been doing in learning about what vision transformers are, and I'll share my results with you guys. My name's Zhao, and here we go. So I'll be going over what vision transformers are, their advantages, their challenges, improvements people have made in the field so far, and conclusion at the end. So, what exactly is a transformer? So, transformers were first presented by the paper Attention is All You Need by a group of researchers at Google, and they were able to show that in NLP that transformers were able to outperform the past dominant architecture of recurrent neural networks, or more specifically, long short-term memory networks (LSTMs), because of transformers' attention mechanism. They were able to outperform these other past architectures and outcompete them. And to give an example of how a transformer works, here is a short sentence. I like to eat sweet foods. Candy is sweet. I like. So a transformer has two blocks. One block is the encoder block, and one block is the decoder block. In short, the encoder learns something about some knowledge we want it to learn, and a decoder generates an output from what it has learned from the encoder. So if we feed to the encoder something about me in the language of English, then and we send in this sentence, I like sweet foods, candy is sweet, and encoder is able to interpret that that I like candy. And so later on, so we'll only be talking about the use of the encoder block in computer vision vision transformers. And so around 4 years after publishing The Attention's All You Need, another team at Google Brains came up with the vision transformer in a paper called An Image is Worth 16 by 16 Words, Transformers for Image Recognition at Scale. And this image is the architecture picture from the original paper, and the results were pretty astounding and revolutionary to the field of transformers, and it began and it's sparked many more research into using transformers in computer vision tasks. So I'll be now explaining what how this process works, how this architecture works from top to bottom. And so to preface, so what is an image? We can represent an image in a three-dimensional vectors, and it's three-dimensional because it has a height, a width, and a channel. Channel is pretty much the color of each pixel. And as you can recall, the original transformers, they take in a series of words, and each word is encoded as some 1D vector. And since the paper says that they want to change as little as possible from the original transformer architecture for NLP, we want to turn this image into something that an encoder block of the transformer can use. So the team at Google thought to cut the image into 16 different patches and represent each word in a sense is a patch. However, since each patch is still in 3 dimensions, we then linearly project it and flatten it into a 1D vector. So as you can see from the image, we have the token 12, and this 12 token is flattened and then linear projected, or meaning passing it into a linear layer and turning it into a 1D vector of numbers. And we do that for each and every one of these patches, and we turn that into an image token. And with the image tokens, the team at Google borrows a technique used in the NLP architecture, to borrow the technique from BERT, a bidirectional NLP tool that was used for natural language processing. It was also a transformer-based architecture, and what they did is prepend a prediction token in front of the image tokens and only classifying the prediction token all the way at the end. And why might we do that? I believe it's during classification, it's just a lot faster, since if you had like an image of many patches, then passing all those tokens into a neural network would take very long, and we don't really need to do that because of the attention mechanism. Like the prediction token at the end, you could basically say it's a summary of what the image is. So after we concatenate the prediction token, we then also want to add a position embedding. This is something they also do in the original Transformers paper. We do this because the positioning of each patch is very important for even humans to classify what an image is. It's like if you scramble a jigsaw puzzle, you won't be able to tell what the original image was. So this just helps out with classifying. So after we have the prediction token added and the positional embedding added to each token, we can then pipe it into our next process, which is the encoder block. So as you can see, the encoder block, you can stack multiple encoder blocks on top of each other. I think they use 6 in this paper, just like they use 6 in the Attention is All You Need paper. To make things easier to understand, let's just black box what the attention module is, what attention is, right, for right now, and I'll explain the whole block first. That way we can understand and not get caught up with what attention is, and we can So after we all have all the pre-processed tokens, we pipe that into a normalization layer, and this basically helps stabilize training and helps the gradients converge faster, which is pretty standard to do. And then that is put into the attention block or module. Just think of the attention module as a way for the tokens to form relationships with other tokens for now. And that output is then combined with the original input. This technique is called a skip connection. We do this because by adding an alternate path for our original data to flow, It just helps negate the vanishing gradient problem. I won't go into what the vanishing gradient problem is. I'll just imagine that you guys can Google it yourself. And after that, we then normalize it again and pass it into a 2-layer neural network with a GLU activation layer. This just helps add nonlinearity to our model and helps it recognize more complex patterns. And as I said before, you can stack multiple of these on top of each other. And yeah, we are ready for evaluation, and hope you guys remembered what the prediction token is. Here's where it comes into play. So with our prediction token extracted from our encoders, hopefully it has learned a bunch of formed a bunch of relationships with all the other tokens, and is now sort of acts like as a summary of what the other tokens are about and what the image is. And that is then passed into a single hidden layer neural network, and we get our prediction class at the end. Now that we have the entire architecture pretty much explained, we can now dive into what attention is. So, in attention, the first step is taking our original matrix of tokens and putting it into 3 different linear layers, each for each of these queries, keys, and values. Each of these have their own layers, and as you can see, it doesn't really change the size and shape of our original data input. And after that, we can now perform the attention function on these to get our attention features. Let's get to the next slide. So I like visualizing it better because looking at an equation like this, it's very dense. I don't really know what it means, but here are some cool diagrams I found. So with the query, we dot product that with a transpose of the key matrix, and that gives us some sort of attention score. And that attention score, because of its shape, we want to turn it back into the original matrix shape of our input. So we multiply that by dot product that with the value, and that gives us our attention matrix, our attention features for each token. If you remember from dot products, you can kind of see, like, because each token is a row, each row is some math is performed with each column in the key, and each column in key is another token. Found a really good table online that helps us solidify this even more. So just ignore the fact that this is for NLP usage. This table is for NLP. We can pretty much use the same table to explain what the vision transformer attention module does. So we have the target word, and that is the query vector, and that query vector is dot product with every other key in our matrix, and that is divided by a square root of dk. Don't really have to worry about what that is, but that gives us our attention score once we softmax it. Softmaxing, what it basically does is that it makes it so all of our values add up to 1, and because of that, the higher score in our softmax value, that is how much more attention the our query gives to other keys, and that is summed up at the end once we multiply that by the value of each token. So in general, just know that this math, these matrix dot products basically gives us some sort of relationship between all of our tokens and the relationships to other tokens. So to help visualize this image is from the original Vision Transformers paper, and as you can see, our prediction token pays a lot more attention. So the dark part is the color, the opacity of this is how much attention our prediction token pays to each patch of our image. And as you can see, the attention our model learned basically only really focuses on the more important parts of our image that is required for classification. And we can see that it has learned. And that's kind of what humans would do. Like if I was looking at an image, and I had to tell what it was, I would really only focus on that part. Like I would only focus on the airplane, not really the clouds part. But the original paper also introduced a very important technique called multi-headed attention. This basically just means that, so our first attention, when I introduced this to attention, that was one head. So we can kind of think of this as if we parallelize the work between multiple different heads at the same time, that gives us a more efficient way to extract relationship features of the tokens. And it helps our embeddings learn different aspects of meanings of things and allows the transformer to capture a richer interpretation of the relationships. So in the diagram of the original attention is all you need, we have a set of different linear layers for each of the heads. However, because at the end we split the resulting matrix of key, query, and values into a smaller section, positional section, we can just have one linear layer for all of the heads. And because of this, different projections for different heads kind of results in a different representations and learning from different positions. Sorry, that was kind of confusing, but just think of it as like if you were to find relationships of two objects by looking at it in different dimensionalities. And because we split up the embeddings at the end, it is pretty much the same computational task as performing attention on one head. Like so. This is a two heads attention, and we split that sequence into two different matrices. So what are the advantages of transformers? To talk about the advantages of transformers, we gotta talk about the perils of the current dominant architecture, which is CNNs. A quick recap of what a CNN is that you have these filters, these kernels or convolutions that you slide across each image, and you do matrix math from sorry, forgot to say, but an image is basically a matrix you can represent it as a matrix, and you slide a smaller matrix or filter across each of these images, and people figured out that it helps different filters extract different information about that picture. So that explains what convolutional is. However, where the neural network comes into play is that the neural network finds the best filters for our task instead of having someone figuring that out, which takes longer. And this has been the dominant architecture people has used for vision tasks. And as you can see, left image is our original picture and the right image is the features extracted. It figured out the left and right edge and where they are. Yeah, so we stack these convolutional neural network layers together, and the first layer would extract lower level features like you can see, like edges and straight lines, and the next one they combine together. You perform convolutions on your resulting convolutions in the first place, and that slowly becomes higher level features. It's like yeah. So some advantages that transformers have above CNNs is that if you looked at this picture of a dog running, the receptive field of a convolutional neural network is quite small compared to the receptive field of a transformer. That's just because of the nature of convolutional neural networks. Your receptive field is limited to how big your filters are. So it's only for figuring out what local features are, how related they are to each other, versus the attention of a vision transformer where one patch from the vision computation could figure out all the other relationships that it needs to know to classify a image. And yeah. And here are some challenges with the vision transformers. If vision transformers did not have any challenges, then it would have completely taken over in the vision world, and where there wouldn't be any more research in convolutional neural networks like LSTMs in NLP. But some challenges is that it is very data hungry, and it is data hungry because it lacks inductive bias that is seen in CNNs, because CNNs looks for local relationships mostly. You can see how relationships between local things usually is more important than global patches in images, as you can tell. However, transformers don't have this inductive local bias. Therefore, this has to be learned, and to learn this, we need a bunch of data. And once we have enough data, you can see. So originally, transformers were given a sequence order, a positional in a sequence, 1D sequence. However, after a bunch of data, it actually learns where it is relative to a 2D space in relative to the entire image. As you can see, this patch learns that I should pay more attention to myself in the middle of this position. And attention, because of all the matrix math, is quite computationally heavy, because there's a quadratic cost with how big and how many patches we have in each image. So to solve these problems, we look for researchers have come up with very innovative ways to go about this. And here's just another table that shows how if we are trained on a very small data set, the regular ImageNet data set, how BIT is the convolutional architecture, I think, and it performs much better than the vision transformer counterparts, but as you increase the amount of data it is given, we eventually outperform convolutional neural networks, the state-of-the-art ones. So here's some of the improvements. So one of the most interesting approach for this problem was the data efficient image transformers, the DEIT, and this basically introduces the distillation token on top of the class token, and it is inserted, this distillation token is inserted into our patches, just like how the class token is inserted into our patches before anything is piped into the encoder block. Basically, what this distillation token wants to do is to learn to classify like a state-of-the-art convolutional neural network. And basically, in theory, the same token is subjected to backpropagation of a convolutional neural network, and it basically kind of sways, because of how attention works, it kind of sways the general architecture of the vision transformers or other patches to behave somewhat like a CNN. Therefore, we call the CNN a teacher of our DEIT model. So because CNNs have inductive bias, our model actually learns inductive bias due to this distillation token. And it is able to perform pretty well with a lot less data. As you can see from the table, with the regular size ImageNet, it was able to perform, the accuracy was on par with state-of-the-art convolutional neural network their convolutional neural network teachers that it was taught from, and performed 10 times or almost 10% more than the regular VIT. And that is what a DEIT model is. And the next model I want to talk about is the swing transformer, the shifted windows transformer model. This was in a paper called Swing Transformer Hierarchical Vision Transformers using shifted windows. And the novelty of this paper comes from the hierarchical approach and the shifted window mechanism. The hierarchical approach is somewhat similar to the hierarchy of a CNN and how that works. And basically what the shifted window mechanism does is that, before I talk about what they do, what's the point of this shifted window transformers? What are they trying to accomplish? So what they're trying to accomplish is create a backbone for computer vision in solving issues of varying image resolutions. If you remember, our original transformer, to evaluate on new data, that data has to be the same resolution as what we trained on. And this model helps with that, and it makes it more efficient to do so. So with the shifted windows approach, we only perform attention on a local window instead of the whole entire image. So this, you're not doing attention on the whole image for every patch. You're doing it only on the local window, and then that is later given to a higher hierarchical layer for classification at the end. And because of this divide and conquer approach to global attention context, it massively decreases the computational complexity. Here is the results from this paper, and SWIN transformers is below, and as you can see, the DEIT is referenced. Let's pay attention to the throughput and the accuracy of the SWIN transformer. And as you can see, it performs a lot better than the original vision transformers, and it's slightly better than the DEIT transformer, and it is quite on par with state-of-the-art convolutional neural networks. And this is only on ImageNet 1K, which is a tiny data set. And if you compare the throughput with the original transformers, it is like 10 times faster than the original transformers. It's able to go through more images than the original, a lot more, which is really impressive. And that's about it for my talk on vision transformers. Hopefully you learned a lot from this crash course, and hopefully you took the takeaway from this is that transformers are not quite there in terms of taking the spotlight from CNNs. We sort of want to, right now, it sort of works with CNNs, and it's quite beautiful how they complement each other, as each of their weaknesses are each other's pros. And I can see that different tasks, if you had a large data set, then you would use transformers, but if you had a smaller data set, you would use convolutional neural networks. So yeah, thank you so much for paying attention to my long spew lecture, and that's all I have.